notice that from two classes block discussion, for a programmer to give this to an AI agent, the programmer should have a theory of the problem. So this can only really be done for tacit knowledge tasks. Explicit knowledge tasks. But there are many, many explicit knowledge tasks because we designed this world we live in to a large extent. It isn't that we are just living in the world that was given to us. We stabilized the heck out of this world. We created the problems that we solve to a large extent. So we do have explicit knowledge, and so we can provide that information. And if you do provide that information, then the question becomes a simple computer science question, the algorithms question, which is, how do I figure out, given the knowledge, how do I figure out my best action? At that level, this is just pure algorithms, pure computer science. The stuff that you have done in 310, the stuff you will do in 450, the stuff you have done in your entire life in general about algorithms. Okay, normally you never ask in a computer science algorithms course, I won't give you the problem, just solve it. There is no such thing. You are given a crisp definition of traveling salesperson problem, and you kill yourself trying to solve it. Do you understand what I'm saying? Right? So that's basically the first side, and then initially, so that's one type. The other type is, no, I'm only interested in essentially dealing with problems where I learn everything that I'm using. So I don't want to take any input from outsiders. I, the AI agent, which will be essentially you focus on learning first. You can think of these as two different complementary approaches. Clearly, this is more relevant for explicit knowledge tasks, and this is more relevant for tacit knowledge tasks. And after that, I'll also say that there is no such thing as pure tacit knowledge task and no such thing as pure explicit knowledge task. You might have a problem where 90% of the stuff you understand, and so you can write it down. A little more of it has to be learned. Do you see what I'm saying? Okay? And in fact, one of the things you can do learning, so in the case of AlphaGo, by the way, any of the chess programs and so on, these are explicit knowledge tasks. The program is not trying to figure out the rules of the game by looking at people playing Go. It has been given the rules of the game. But having given the rules of the game, finding the optimal, actually winning strategy is extremely hard computational problem. Do you understand what I'm saying? So it's like a funny thing that a lot of people forget, that even if I give you the problem, solving it can be undecidable from a computational perspective. Okay? So this approach sort of focuses first on the search, thinks that I will figure out how to do the learning part later. And this approach sort of focuses only on the learning part and assumes that I will eventually do reasoning. So people in this world will say things like, one of these days AI agents will do reasoning. That's because they have not done any reasoning in their lives. They are only focused on, for example, visual tasks, and where there is no explicit knowledge, and so they basically had to learn whatever they had to use, and they're trying to get from there towards, actual reasoning performance and so on. On the other hand, these are the guys who say, one of these days we're really going to do learning. Okay? It's worthwhile understanding that the textbook is written with this direction. And if you just take a pure machine learning course, it has this. It's not because reasoning is not important, it is the thing that we haven't gotten around to doing. Every scientific discipline pushes some things under the rug. Every scientific discipline strand pushes some things under the rug. It's important to figure out what is pushed under the rug, so that you won't just be one more of the people who repeats what they read in the popular press. Okay? So, okay. There's a whole entire discussion about this. I don't know probably in the lecture that you saw about if one advantage here is that the humans are giving the representation. Somebody outside is giving the representation. They are telling you what are the relevant features, what are not the relevant features, etc. Okay? That makes it easy, A, to first of all, you're dependent on the human civilization's acquired knowledge. And B, if you fail and you need help, you can go back to them and talk to them in the language of the features that they provided you. Because they actually understand that part. Whereas if you learn your own representations, then if you fail, and if you come up with an answer that I don't make sense of, and I say, why did you come to this? And you will say something that will be gobbledygook, because you're talking in a completely different language. Language is about shared understanding. You see what I'm saying? The reason we can't go off to other worlds and talk to them, is normally because language difference. The shared understanding sometimes might be you can point to things. That doesn't require language, and that might help you kind of do some communication. So in general, the problem of interpretability that has become a huge thing in AI of late has to be understood in terms of this column. It's only if you learn your own representations, you the AI agent, starting from raw data, then you may well be doing stuff that I have no clue about. Then I will ask you for explanations, and those are explanations that are harder to even understand. Those would oftentimes be pointing explanations. And in the context of images, sometimes pointing explanation is at least possible. You'll say, why did you think of this as the Alaskan Husky? You say, and then show what I think is snow, and I say, you bozo, that's snow, that's not dog. Just because there is snow, that doesn't make the dog Alaskan Husky. Easy enough. If on the other hand, if you ask, Rao, why did you bring bicycle today? For example, okay? I have to make an explanation for my decision. And if I have to point, I have to point to the space-time tube of my life. Do you understand what I'm saying? Let me now play my life in front of you. That's an extremely inefficient way. Imagine anytime you ask somebody to explain something, they'll say, now let me play a movie. And then you might figure out. You have to assume that the human civilization really happened because we could avoid this kind of pointing explanations in most of the cases. Okay? And so that is this issue of interpretability problem, and the fact that it's more of an issue here than here. Okay? Yes, there was a raised hand.
My name is Avtar.
Okay.
My question is that then is it like can we know that there might be autonomous agents that have been just learning through the second part? Like
Yeah.
For focused learning. So can they be autonomous, or there has to be some set of ground rules so that?
No, that's the thing. The pure version of this is they just learn. In fact, Yahoo would basically say, an AI agent watches YouTube videos.
But then
I think you should say Facebook videos, but somehow it says YouTube videos. And then they just learn. Because, in fact, funny thing is, space-time tubes of normal life exist on the YouTube. And our life is too short that we don't watch them. Right? But a program can just watch large numbers of space-time tubes and try to make some sense out of it.
but can it be completely autonomous after some time? Can we rely on that completely because we don't know how it is?
Okay, by the way, this is the beginning of the course. Huge number of problems are open problems. Otherwise, why introduction? I would be doing one of these executive courses where I say everything has been solved, you just give me the money, I'll solve the problem for you. Okay? These are all open problems. Okay? And there are no pat answers to this. In fact, one of the interesting things that I don't even want to get into, actually went away, is there's a beautiful slide that I hid called the Nicaraguan deaf children problem. Amazing issue, where children basically devise their own language left to themselves. They are deaf children in Nicaragua. During the wartime, this orphanage was abandoned, and the children designed their own language. And that language has no connection to any sign language that existed before. And yet, interestingly, people were able to learn that language. What's even more mind-blowing is that in the space of all possible languages that you can have in the universe, that sign language is closer to human sign languages than anything else you could have come up with if you just basically a randomly generated language. That blows your mind. To some extent, we all share, in essence, the same kinds of mind-brain, and so there are some interesting limitations on the kinds of things we can come up with. You know, we all complain to each other saying, oh, this language doesn't make sense, my language is much better, etc. All human languages make sense. And they're actually a small, really small subset of the possible languages. Okay? So that's actually an interesting question about why the, you know, if you were to think in terms of whether or not kids are learning this way or this way. What would you say, by the way? Are kids learning this way or this way? How many people think the kids are learning this way? I mean, kids in general, humans, let's say humans, these are kids. How many people think this way? Why are you taking this class? I'm telling you, you shouldn't be told. You should just observe the world and figure out what AI is. You see what I'm saying? As somebody said, human learning is in between. Some pieces are from this side, some pieces are from this side. We are not curious. And it's worthwhile keeping that in mind. So our plan of action for this whole semester is we'll start with the inference focus and then sort of interleaving some learning into it, because that's more or less more of the left-hand side, but we'll shift into right-hand side sometimes, especially when there are tacit tasks for which I can't actually provide any reasonable features. Do you see what I'm saying? Things like a feature like the number of pieces left on the chessboard is a semantic feature. A feature like age is a syntactic feature. And what computer vision people would do when they're giving hand-coded features would be in terms of things like edges and so on. That's because they don't understand. We don't understand how we do vision. So you might as well leave it to the computer to figure it out as a learning task. But there are many other things for which we do understand, for example. Okay? And so there you can provide the features. Okay. So then that gets us to problem-solving agent, the atomic agent. And so in essence, as I mentioned already, so in some sense we are looking at this, the architecture. And so we assume that by default we'll assume that the states are black boxes. But once in a while we'll provide structure to it. But even if we provide structure, it is only to make your code easier than anything else. Okay, because the program, the search algorithm doesn't look at the structure much. Okay, this is actually a tricky part. You have to really try to understand before the search algorithms are over that none of your search algorithms, the basic queue manipulation is the big difference in the different search algorithms. You understood that, right? The difference between depth first and breadth first is the way the queue is manipulated. The queue contains a bunch of thingies. They don't look into the thingy to see what it has. They just basically, breadth first says whoever is in the, you know, whoever got into the queue first will be taken out first. Depth first says whoever is the top of the stack will be taken out first. They don't look at the representation. Okay? So that's why these are actually problem-solving agents. You should think of them as basically being blind to the representation of the state. Okay? And so you are given an initial state, which is some indivisible state. You're given a child generator function, which is a piece of code that takes a state and gives out states. And you're given a goal test function, which takes a state and says, yes, it's a goal, no, it's not a goal. These are the only pieces you are given. And in fact, from the data structure point of view, we'll come to it in a minute, but instead of the search algorithms actually look at what are called nodes. And a node is a data structure, one slot of which is the state. The other slots basically in that node data structure are bookkeeping stuff like which node was expanded to get this node. And as we go into things like A star search, what is the total cost you spent to get to this node? And to understand node and state are different, you can have two different nodes with the same state, but they have different costs. In an undirected graph, you can go from A to B, go back from B to A, come back again to B. You now have two search nodes with B as the state. One is a Bozo state, right? Because it basically went back and forth. But it's a distinct state. And in fact, from a computer algorithm point of view, keeping track of this kind of loops becomes very important in graph search. Otherwise, you do very inefficient search. You see what I'm saying? Okay, so that's what we're going to do in terms of the problem types, problem solving agent. Yeah, in terms of problem types, essentially we will mostly be looking at deterministic and accessible, which is really a single state problem. That basically means the goal at any given time, the agent thinks it's in a single state. It can be indivisible, but it's a single state. But that essentially assumes that the agent is able to look at the state and recognize what state it is. If it is partially observable world, at any given point of time the agent doesn't know what exact state it is in. What that means is it thinks it's in one of many different states. Not knowing the state only means there is a disjunction in the number of states that you think you might be in. If you don't know anything at all where you are, and if it's a state space of size 10,000, that means you think you're in one of the 10,000 states. It's not infinitely large uncertainty. Okay? And so in fact, most of the search algorithms that we look at will also work for inaccessibility. So in fact, most of the ones that we look at this class and next class will work for any deterministic problem. Deterministic means an action gives rise to a single state. Action applied to a state gives rise to a single state. What that essentially means really is there is a node NS, node n corresponding to the state S, and then you apply the child generator function to it, and then it gives rise to a whole bunch of nodes. And each of them kind of correspond to doing different operations. If you do O1, if you do O2, if you do O3, if you do O4, those are the states. Even the operators themselves are essentially indirectly represented in a problem solving agent. Okay? So that's where all that additional bookkeeping went away. So in fact, the point is, the moment you have inaccessible or partially observable world, you still can do the same algorithms that we are talking about. In fact, the A-star search will still work, except instead of searching in like a space of size S, if the S is the number of states, it has to now search in the space of all subsets of the set of states S. Did people understand what I just said? How many subsets are there for S things? 2 power S. In general, by the way, a good heuristic is for the next several classes, if I ask a question and it requires some number, say 2 power. And you'll be right. And you'll be right. Okay? So if you have S states and you can't see which state you are in, then in essence you are searching in 2 power S sized space. Now, if in fact these S states are represented in terms of n state variables, such that S equal to 2 power n. So really, when you lose your eyesight, you are searching in 2 power n states. That's what losing eyesight means. Suddenly you now are searching, your friends are searching in a much smaller space, that's the one that's accessible to them. You are stuck with having to search in a much larger space. Sometimes, in fact, you may not even be able to reach goal, and if you can reach goal, it's a much harder search for you if you don't have IC. That's a computational way of understanding what happens when you lose census. Okay? Somewhere along the line, I just said, yeah, so 2 power n is the evil every CS student's nightmare should be made of. So if you wake up with cold sweat in the middle of the night, it better be because you dreamt of 2 power n. Okay? So that's, in general, 2 power n is bad news. Okay? Okay, so search in the deterministic environment. So now that we set it all up, right, basically problem solving agent, so if I'm searching the space of Romania map, for whatever reason textbook uses Romania map, right, and formulate the goal, let's say be in Bucharest, of course, where else will you be if you're in Romania, Bucharest, right, and then formulate the problem, the states are the various cities, okay, and the operators are drive between the cities. Notice they're saying formulate, formulate, formulate. It's because this is an explicit knowledge task. And you are providing the knowledge about the task to the program. And you can provide it in better representations and worse representations. That's the question that our friend asked earlier. Maybe there are representations which are kind of too fluffy in the sense they allow for many, many states that are not actually legal at all. And then the search algorithm will get stuck in those. But anyway, so found the problem states are various cities, operators are driving between the cities, so you assume there are roads between them and you just basically drive between them. And the final solution is the sequence of cities are basically the roads, if there are multiple roads between the cities, then you'll also talk about sequence of roads. But in the map that they had, this is the way their map is, right? And so if I am at Arad, see Arad, and I want to go to Bucharest, then I'm trying to find the sequence of roads that I have to go, sequence of intercities transitions I have to make to get to Bucharest. Okay, so one of the interesting things is that by the end of this class, you should all be, especially this set of classes, you should all be into Romania. You should be Romania experts. So a while back, I was coming back from India a couple of weeks back, and on the flight they show the map, and I saw this. And I had this incredible urge to start doing A-star search. I couldn't tell why. Why suddenly? You might think you're a bozo, you always want to do A-star search. But really, it's because I saw Cebu. And you know that Cebu is there somewhere. Cebu, there you go. So whenever you see Romania, you should do search. Now onwards. Interestingly, actually, there were all these, this textbook has been the most influential textbook in intro to AI for quite a long time, and there were all these pet theories that various people made up as to why Romania map. And maybe Stuart Russell is Romanian. Oh no, he's as English gets. And maybe Peter Narvik is an American. So cool. Americans can be from anywhere, so maybe he's from Romania. Turns out he was also not from Romania. So I was talking to Peter and he said, we just wanted to come up with a map that not too many people understand, so that they won't say, why not this other road? Why not this other map? You see what I'm saying? So he just assumed basically that Romania, not too many people. So people in Romania must be asking all these questions. What bozo? Who would go from Arad to Faradas to Cebu at all? This is a bad road, It's like too many potholes there. Okay. So anyway, that's that. So single state formulation we have already understood, and then so here is a thing that you have to understand, and in fact you will be made to do like a bunch of problems on this because this is an art form. Science can be taught, art needs to be practiced. Okay, an art form is if you know the problem and you want to give it to your algorithm, what should be the best representation of states? In fact, again, a friend talked about it, that there could be multiple different representations. Are there better versus worse representations that you could come up with? I'm just depending on you. So this is not about AI. This is about you giving a more compact representation to your search algorithm such that you get done faster. You see what I'm saying? Okay, so in general, in thinking about this, you basically realize that actually, in case you should understand, right, there is no actual single point in the world called Cebu. There is no single point in the world called till P, right? They basically just abstract out and say the center point of each city, which is arbitrarily defined, is considered that city. Right? And so it's an abstraction. Okay? So you abstract the real world into states. Abstract real world into states. You abstract real actions into transitions. You do all these abstractions. And then you let the program figure out the combinatorics, which is what a good computer scientist always does. Okay? And so figuring this out is not obvious, and then once you come up with the solution, once the algorithm comes up with a solution, that just basically is an abstract solution. If I just tell you, oh, go from Arad to Cebu, and then Rimirchu, and then whatever this is, Piraeus, and then to Bucharest, there are all sorts of crazy things that might be happening on each of these roads. You see what I'm saying? I'm just abstracting all that out. So the actual trajectory that the agent will take would be many trajectories would be correct with respect to this abstract thing. Do you understand what I'm saying? Okay, so that's the notion of abstraction that they talk about, and this is basically worthwhile keeping in mind because you will be made to do some number of examples on this. Again, this is a funny thing. On one hand, we are saying problem-solving agents don't care about the internal structure of the state, but on the other hand, we are saying actually it's useful to have some kind of a representation so that your algorithm, you have to write the child generator function, you have to write the goal test function. You, the designer, and you might as well have a good representation. It's almost like saying 310, come up with a good data structure. That's what we're doing here. Okay? And so, if you go to something very different, like 8Puzzle, and first of all, let me point out that one of the biggest success stories of graph search is really pathfinding. Right? Your basically your Google Maps, etc., is very quickly recomputing paths when you say I want to go from here to here. And it basically has the map. It's not quote unquote learning the map. It's not trying to say, okay, suppose I kind of make this road that is between two cities which are across from each other. Like for example, suppose there's a direct road from South Rim to North Rim. Then just take that. That doesn't make any sense. By the way, those of you who are new to Arizona, South Rim to North Rim, as crow flies, is 13 miles. As you drive, it's 220 miles. Because you have to come out of the Grand Canyon and go all the way to the other side. There is no road. So essentially what Google Maps does is it actually looks at the roads that exist, that we made, and then it's figuring out. And different roads have different costs. For example, the interstates might be faster, and some minor roads might be slower. And one of the more interesting things that it does learn, actually, is congestion. You understand this red stuff on the maps? That, roads are not made with red stuff. And the red stuff goes away. Right? And it's basically because it's learning what roads are congested. Do you know how it is done? What? Do you know how all these programs figure out which roads are congested?
Depends on the other units.
One person who wants to give a name, yes.
Using data from us, it tracks our phones.
Exactly. Crowdsourced data. If you want to stick it to Larry Page, leave all your cell phones at home. Right? Then everything looks good. And you can say, you bozo, notice that there are no cars moving in front of you. If you don't, basically they are looking at the cell phones. And the cell phones you are a sensor. Your cell phone is a sensor. It's always giving away information about you. In the old days, it was only giving your coordinates. Now it's giving your age, your interest in different things, etc. That's how advertisements are being done. Okay? But that's basically what happens, crowdsourced learning. It's not like major, learning by exploration. Okay? Anyway, so those are useful. So you can actually compute things like, edge costs directly. Okay? So then this actually the one representation, there are other representations for one. So the most obvious representations people tend to think about for this is essentially, of course, they will say where each of the tiles are, what is the coordinate position. But the most obvious representation people tend to think of are the actions being move tile 3 from where it is to this position. That's what you would come up with. That's exactly where our friend's point comes across, which is most of the actions you can't do. Because you can't move 3 into 7 because they're both full. Really the only movement that is allowed in puzzle problems is blank moving. It's strange. You think actually, oh, I can move 4 here. That's not a good way of thinking about it. You say blank moves into something next to it. So sometimes good representations can be slightly counterintuitive. The algorithms will work even if you came up with a bad representation. They'll just be less efficient. You understand what I'm saying? Okay? So this is a nice representation essentially where the operators are moving the blank left, right, etc. As if blank has its own life. It's moving around. It's obviously a counterintuitive way of thinking about it because most people think they are actually moving the tile because they're holding the tile and moving it. But it's much better to think of it as you're holding the blank and pushing it into the tile. And then the tile comes into the blank space. So that's the art form. Okay? And as I said, of course, 8 puzzle actually is one of these bad puzzles where its search space is split into multiple disconnected counties. Okay. Okay, here is robot path planning. In general, in fact, one of the very interesting questions is path planning in general. You understand, even map following is a path planning problem. But one of the other interesting things is when there are, things like this, when you have obstacles in a 2-dimensional space or a 3-dimensional space, and the robot has to go from this place to this place in the shortest way possible. This is what all the mobile robots have to do. That's a search problem. And if you have a reasonable robot, for all intents and purposes, you can assume it's a deterministic movement. When it tries to go forward, it actually goes forward. If you have a cheaper robot, then when it tries to go forward, sometimes it goes forward with like 80% of the time it goes forward, 10% of the time it goes left, 10% of the time it goes right. If you have a really cheaper robot, 80% of the time it goes forward, 9% of the time it goes left, 9% of the time it goes right, 2% of the time it blows up. Right? It can happen. It's a really bad robot. Okay? And that's basically then uncertainty. In general, most people assume that if they spend money, they have good mobile robots, and so the find path problem would then be in a large